All right, hi, my name is Richard Mills from Argonne National Laboratory. I'm one of the PETSc developers, and today I'm going to give an introduction to nonlinear solvers and talk about how to use them in the PETSc tau package. Let's see. Okay, so systems of nonlinear equations of the form that I'm showing right here, this very general way of writing them, where F's mapping from Rn to Rn. These arise in tons of different settings in computational science. And unlike what you may have seen from like some of the linear solver content this morning, direct methods for general nonlinear systems don't exist. So iterative methods are a requirement for solving them. Probably the simplest possible way of solving these iteratively is just with Richardson iteration, which again you may have seen in a linear algebra context, and you can very easily generalize that to a nonlinear setting where each iterate is basically some constructed by taking the last iterate and adding some multiple of this residual to it. This is a really simple method, but it's got linear convergence at best. So some methods that may do better are nonlinear Krylov methods. So some of you may have attended the iterative solvers talk this morning where they talked about Krylov methods for linear systems. You can actually generalize these to nonlinear methods as well, and there are things like nonlinear conjugate gradient, which mimics the linear conjugate gradient, forcing each new search direction to be orthogonal to previous directions, or nonlinear GM-res, or the closely related Anderson mixing, where you're minimizing this residual by forming some linear combination of previous solutions and solving this linear least squares problem. And these can have superlinear convergence. But really the workhorse that we see in nonlinear solvers is Newton's method, basically the same thing that you saw in your Calculus 1 class when you were a freshman in college or a high school senior. So again, Newton's method is solving a nonlinear system. We've cast into this form where we're trying to find roots of the system. And so the way Newton's method works is basically you just keep finding a bunch of linear approximations to your system. You linearize, and then you get the best solution from that linear system, and you update. Where we've written things in this form here, where the Jacobian is this matrix of derivatives. And the reason why Newton's method is so popular is probably because it is quadratically convergent when you get close enough to a root. And here I've just written an example of what it looks like for doing a nonlinear Poisson problem. So high-performance nonlinear solvers for doing things like Newton methods are available via a bunch of different packages, like the PETSc tau package, also the sundials package, and Trolinos has a couple of different packages inside it that do these. But here we're going to focus on PETSc. So I should say I should spend just a minute saying what PETSc is. PETSc is the portable extensible toolkit for scientific computation. It nowadays includes a toolkit for advanced optimization, and it's something that originally was written for facilitating doing PDE-based simulations, but since then it's grown to do a whole lot of other things as well, although PDE kind of stuff is still kind of our main bread and butter. And there are a lot of kind of different levels of complexity in the library. Down here there's some very low-level things, like vectors, various kinds of matrices, and algorithms for operating on these. And then above that, preconditioners, Krylov solvers, the nonlinear solvers we'll talk about today, and then sitting on top of that, things like time integrators and optimizers. And here's just another view of basically the same kind of thing I showed in the last slide, just actually identifying particular components of PETSc and just sort of how they are related to each other in complexity. And the thing to note is, like here we're going to be talking about the nonlinear solvers. But these things, the nonlinear solvers, the SNES component, that's a scalable nonlinear equation solvers, depend on all these things below them. And this will be important if we get to some of the bonus GPU material that we may talk about if time permits. Before diving in to the nonlinear solver content, I just want to note that PETSc really is designed as a platform for experimentation. really, optimal solvers have to consider the interplay among the physics, the algorithms, and architectures, and this need motivates several elements of the PETSc design philosophy, some of which you'll see a little bit in the hands-on exercises. So what we strive for in PETSc is to be able to have algebraic solvers that are very composable, hierarchical, nested, extensible, so you should be able to take individual solvers and combine them in arbitrary ways, because this is actually pretty important for solving some kinds of problems. And also to facilitate experimentation, you can pretty much set all of these configurations at runtime, and also control a bunch of aspects of the data layout, and this extends to like how we do things like run with GPUs. All right, so I already talked about what a Newton method was and showed the Calculus 101 definition of what that is. In what you would have seen in your calculus course was probably was exact Newton, where we linearize and then we solve exactly this linear system. But in practice, incurring the expense of an exact solve for a Newton step is often not desirable. And you usually want to use an inexact Newton method, where you find some approximate direction that satisfies this relationship here, where f prime is the Jacobian. For some forcing term that you choose, that you can just choose it statically, or there are some different adaptive methods in PETSc for choosing that. And then to get these approximate Newton directions by inexactly solving this system, most people use the Newton-Krylov methods, where we use a Krylov subspace projection method as the inner linear solver. These are pretty robust and widely used, and PETSc provides a really large range of Krylov methods and linear preconditioners that you can just access via runtime options, and we'll see a little bit in the hands-on how you can do that. The other thing that I should mention is, I mentioned at the beginning was Newton methods are great because you get quadratic convergence, but you actually only get quadratic convergence when your iterate is sufficiently close to the solution. Far away from the solution, the computed Newton step is often too large, and so it's too large, and you waste a lot of time solving that step, as we showed previously when talking about inexact stuff. So in practice, some globalization strategies usually needed to expand the domain of convergence. There are several options in PETSc for doing this. The most common one and the default is a backtracking line search. So what that does is it just replaces the full Newton step with some scalar multiple of it, and you do this by introducing some merit function with a form like this. And then you want to approximately solve this minimization problem, but you don't actually want to solve it very accurately because that's expensive. You just need to do something to get sufficient decrease. And you build a polynomial model for doing this. In PETSc, the default is cubic, but this is, again, something that you can just change with our runtime options. You can just change the polynomial order there. We're going to be using PETSc's SNES component, the scalable nonlinear equation solvers, and since we don't have time to really write code today, I'm not going to spend much time on this, but I wanted to just talk about what this looks like if you're a user. The interface is based on callback functions, where you have a form function, that's your nonlinear function or residual, and a form Jacobian. That's actually an optional thing. And when PETSc needs to evaluate this nonlinear residual f, it's going to call the user function that's defining your nonlinear problem. It's going to call whatever we've set by form function. And then the user function is going to get application state through this context variable, and PETSc never actually sees the application data. So what this actually looks like in the code that we're going to run, we'll see an example. It has a C prototype that looks like this, where we're just passing in a current solution, a residual, and then there's this context to have kind of application-specific stuff that the function may need to know about. Similarly, the Jacobian interface looks very similar to that. Alternatively, and that's actually what we'll use in the hands-on, we won't even use a code that defines its own Jacobian. We're going to have PETSc calculate one using a sparse finite difference approximation, using some matrix coloring. So we're going to do some hands-on exercises with tutorial example SNES EX19. I apologize for the very uncreative historical naming of the examples, but this is EX19's been in PETSc forever. It is actually what is run as part of make check when you install PETSc yourself and want to verify that it's working. What it's doing is it's solving a 2D steady state non-isothermal lid-driven cavity problem. This is a classic CFD benchmark. And it's doing this using a velocity vorticity formulation that was contributed by David Keyes. It's just doing finite differences on a logically regular grid that's parallelized with PETSc's DMDA. DM is PETSc's domain management object that does a lot of helping you manage your grids and objects that live on those. We're using the very simple one that's the DMDA variant, where DA is just a sort of a distributed array. And this example doesn't provide an analytical Jacobian, it's just calculated using finite differences. So that's what we'll be running. And you know, I had talked a little bit about what this looks like as a user. I just show here some examples that if you want to, you can open up the ex19.c file that's provided in the examples directory for our track and look at this. But you know, I just show here some little highlights like what the application context looks like. It's pretty simple for this problem. And then you can look at what the form function looks like, and it's just doing finite differences here. So it's a pretty simple thing that we're going to be working with. Okay, so let's try to move to some hands-on exercises. And I'm going to actually take a poll. I'm not sure how many people find it helpful for the instructors to kind of like, you know, kind of go through this in real time, kind of demo the hands-on problems. Do people like that? Or okay, so if you like that, enough people like that, I will do that. And if you don't like that, just ignore me and you know, just work on stuff. And then if you have questions, ask in the Track 5 numerical Slack, and like Satish or Todd may be able to help you, or you can just bug me. But I will try to go through these. And what I should have done already was I should have, I'm on the Theta GPU service node, and I should have already asked for this, and I didn't. But let's see, hopefully it'll start soon. And if it doesn't start, in my case, actually, the first part of this, I can actually just run the same exercises on my laptop, so I'll do that if I don't get a session in a bit. So anyhow, let's, I guess we should go in while we're waiting for that to start. So on the Math Packages training page, which hopefully you've all been able to find, under the navigation, there's lessons, and then we'll be using the nonlinear solvers with PETSc instructions here, which are actually pretty self-explanatory, and you don't really even need me to go through them, but I'll go through these. So let's see, do I have a session yet? Okay. Okay, so I have a session, and we're supposed to do a module load. I believe it's already in my history, so yep, okay, so this is the module load command that you should do if you haven't done that yet. So now as soon as I cd into my correct examples directory, and okay, yeah, I'm in the right place. Okay, now we are ready to start doing the hands-on. Okay, so one of the first things that we want to do is just run EX19 on a single MPI rank with some basic command line options, and I'm just going to copy and paste all of these. Come on. So I'm going to copy and paste this into here. And so what we get with these options is this output that is not really particularly exciting or edifying. It shows that I'm doing a bunch of Newton steps, and I see the function norm at each step. And let me switch back to my slides for a second. I have an explanation here of what these command line options are, because we've stuck a lot on here. The SNES monitor says, hey, we want to show the progress of the SNES solver. That's why we're getting those residuals at each step printed out. I also want to be told the reason for when the SNES object converges or diverges, so I've added this. I mentioned that we use a PETSc DMDA for kind of helping manage our parallel problem. This sets the initial grid size in the x and y direction, and then I'm telling it how many times I want to refine that before I create the grid that I'm going to run on. So we're going to be controlling the problem size by adjusting this DA refine to. And then this is a driven lid problem, so I'm setting this dimensionless velocity of the lid to 100. And then there is the Grashof number, which I'm setting to 100 to start with. And these things will control the nonlinearity. One thing I'll note is there are a whole lot of command line options you can use in PETSc. One of the elements of the PETSc design philosophy is really extensive runtime customizability, and we have a -help option that enumerates and explains the various command line options available. And I note it does this in a context-sensitive way. So if you've specified some like a particular kind of preconditioner you want to use, and you add -help, it'll tell you like more options specific to that preconditioner, for instance. So, okay. So one thing we want to find out is what is this SNES solver that I just ran actually doing? So I can add another option, which is SNES view. And at the end of that, it will print this out. And let's see, I don't have a, I wish that the display was higher resolution so I could fit all this on here. But it prints out a lot about what solver hierarchy has been used. And in this case, we're doing something pretty simple, but it's worth looking at this to just understand what PETSc is doing. So I've got a SNES object I'm running on one MPI process. The type is Newton LS. The LS is line search, because I'm using that and not some other globalization method. There's some stuff about the tolerances here. There's a note that we're building our Jacobian using colored finite differences. There's information about what exactly our line search object is doing, and then what the underlying KSP object, the Krylov space solver, is being used to solve the linearized system that we get inside the Newton solve, the restarted GMRes. And then we're preconditioning that with an incomplete LU factorization with zero fill-in, and there's even some information about the size of our matrix and what kind of, how it's stored. It's using PETSc's AIJ format. So there's a lot of information here that can be very helpful when you start doing very complicated compositions of solvers that we will explore a little bit. Okay, so let's get back to, actually I think I want to be back to my, back to the hands-on examples page. So we looked at the, ran something, looked at the options, and then we've looked at the SNES view output. It's something like what I got here. Okay, so one thing I noted, PETSc has a lot of runtime options, and there are a bunch that we're going to want to use all the time. You can set all these to the command line, but you can set them also from input files and shell environment variables. To make it so there's less typing, I'm going to actually set an environment variable. The PETSc options environment variable. I do not know why it's not letting me. Oh, okay. All right. I'm going to set this. I'm just going to copy all this into here. So now that I've exported this into my PETSc options, every time I run our EX19 executable, it's going to use these PETSc options. So everything else that I want to specify additionally is all I have to type. Okay, so I've done this and I've added KSP converged region to see how and when the linear solver fails. And I also added a log view command to write PETSc performance logging to a file. PETSc's actually got a pretty detailed performance logging framework built in. These are actually really useful for a lot of stuff. I don't have time to really explore these, except maybe if we get to a little bit of the bonus content on GPUs, I'll talk a little bit more about that. But right now, we're just going to use this performance log file to find the overall wall clock time, which we can find just by executing this particular grep command on this log.txt file that's created. The first number you'll get is the total runtime in seconds. So, okay, now let's start talking about maybe something more interesting than just running the example I ran. First thing I had mentioned in my slides was talking about exact versus inexact Newton methods. The SNES view output that we just looked at showed that we're running an inexact Newton method. That's the default. To run with exact Newton, we're going to say that the preconditioner type we're going to use is not an incomplete LU factorization, but in fact, we're going to just run with a full LU factorization. So the preconditioner actually just completely solves the linear problem. So we're going to do that. So I will just run this. I'll run both of these. I'll just copy these and run. Okay, so you can see, yeah, we're doing an exact solve, so the linear solver always converges in one iteration because it's actually a direct solver. Okay, so that worked, and oops, I meant to copy this grep command. Okay, and so I grep it, and we're doing it in like 0.74 seconds. Okay, so generally you don't want to be using an LU solve. You don't need to use a direct solve inside that inside your Newton solver, right? So let's try using the default iterative solver with some different tolerances. So we'll start with this fairly tight tolerance, and just put this in here, see what it does. See, it takes about the same number of Newton iterations, but we're doing a lot more linear solver iterations, right? Because we're using an iterative solver there, not a direct solver. And I'll run this grep command again. So it's actually, in this case, this is taking a little bit more time than the LU solver was. And something that I encourage everybody to try now, if you've been able to follow along, is try running this, but just varying the tolerances and just decreasing by orders of magnitude and see what happens to the performance. So I'll go from 1e to -8 to like 5, and we'll see what happens. Okay, so we had to do fewer inner solver iterations, right? And so it should be quicker. Yeah, okay, so under half a second there. So that's faster than the LU solve. And actually I'm a little, I want to make sure you've got time to do some more interesting things. So I encourage people to, if you have time now or to come back, you can mess with this. But I'm just going to jump down to using a really, really coarse tolerance here and see what happens. Okay, so I ran with a very coarse tolerance. You see, this actually required more overall Newton iterations. But, there are very few linear solver iterations happening. And so actually, I'm solving this, this is by far the fastest solution time. So I'm getting worse convergence for my, I'm getting it's sort of worse numerics for my Newton solve. I'm having to take more outer iterations for this, but in the end, I'm actually getting the answer faster in terms of wall clock time. Okay, so that was just the first thing I wanted to talk about. It was just inexact versus exact Newton solves. And actually, they're, in my experience running some really big applications, I've done a lot of like very large, say like groundwater flow and reactor transport problems. Choosing that Newton tolerance, choosing the inner tolerance for your Newton solver is, for your linear solve inside your Newton solver can be really important for actually getting the best performance. Okay, so so far we've just been running on just one core. Let's try to scale up the grid size for a model problem, and to do that we'll also run in parallel because otherwise this takes too long. So I'm going to take the linear solver defaults and increase the size of the grid, and I'm also changing the KSP type. Before I was defaulting to using a GMRes with a restart size of 30. That actually fails in some cases unless we increase the restart size and make it more expensive. So instead, we're going to use a biconjugate, a bi-CG stab solver that's biconjugate gradient stabilized. And we'll just try running this on the larger grid. In fact, we'll start actually just with one refinement, the same size we were doing, day refine 2. And what we want to do is, and while that's running, we just want to see what happens to the iteration counts and the execution times as we keep making the grid larger. So, okay, get our execution time. Now let's refine everything again. And let's refine things yet one more time. This will take a little while. And so the thing to really notice is as I refine the grid each time, you want to look at the number of linear solver iterations. It really it starts to grow quite a bit, and if we kept going, it would grow to be really very large, the number of inner iterations that we're having to do. So what we're seeing is that even though a Newton solver actually has mesh independence, like that is as you refine the grid spacing of your problem, we're seeing basically the same convergence behavior for our Newton solve. The outer solve, that's the Newton steps, takes about the same number of steps. But the inner solve, for the linear solve, that is not mesh independent, and we're having to do a lot more work in the linear solver as we've increased the problem, many more iterations inside there. And so the problem is really we're using something that is not an algorithmically scalable linear solver. We want to use something like a multi-grid solver. So we'll just turn that on by saying, okay, this time we want our PC type to be multi-grid. And what this will end up doing is giving us a geometric multi-grid solve that uses V cycles. And then, okay, so now we've gone from hundreds of iterations to, like six or seven in here. So this is really important. This is why people want to use multi-grid. So let's see, I ran that for, so that was running it for, the largest problem that we had done, the DA refine 4. So you can see it's really, if we ran it with 3, you'd see basically the same numbers for the linear iterations that we take. So that's the great thing about multi-grid. Okay, so the takeaway here is that the combination of the fast convergence of a globalized Newton method and a multi-grid preconditioner for the inner linear solve can give us a powerful and highly scalable solver that we don't get when we're just trying to do something simple like incomplete LU factorization for our preconditioner. So that's one of the important things that I wanted to get across in this lecture. Now let's see what happens if we start increasing the strength of the nonlinearity. So that's, again, controllable by this Grashof number. And let's see, this is basically what we were running before. So just run it again. All right, and then let's see, let's crank this up by an order of magnitude, see what happens. Let's see. In fact, here, I'm just going to go to, okay, I've cheated and I already know what's going to happen. And I will go to this higher Grashof number. I find that when I crank it up to about here, then we start, the solver starts to have trouble. In fact, okay, what happened here was when we went back to just using the default linear solver, it can't converge there. It did 10,000 iterations, and it's basically just stagnating. So we need a more powerful preconditioner. And you see this is the linear system inside gets harder as we increase the nonlinearity of the problem. So we can do a little bit better, again, by, this will work okay if we just say PC type MG, then it should work okay. All right, so more powerful preconditioner helps us go a little farther with that. And let's see, and then I wanted to try, okay, but let's try, cranking things up just a little bit more with the nonlinearity. I mean, this is very close to the Grashof number we were running with before. Okay, but we increased that nonlinearity a little bit more, and even though we went from using the ILU preconditioner to a geometric multigrid, we're still having divergence because we can't solve that linear problem inside. And in fact, one thing that you might, okay, so maybe this is a problem with our multigrid solver. Let's see. Let's try doing the same thing that we just did and running it with LU. So I'm using a direct solver, which is going to be more expensive than an iterative solver most of the time, but it's eliminating any issue really that has to do with my linear solver in here. So let's see if the problem is the linear solver or the nonlinear solver. I'm getting convergence with this. Okay, so we're able to solve the linear problems exactly, but we still have problems with divergence because we've set PETSc to stop after it's tried running 50 Newton solves, which is a lot. Sorry, Newton iterations. All right, so we tried that, and we got something like this. Oh no, sorry, I'm a step back. We tried brute force and tried employing PC type LU, and so eventually you reach a point where this is really beyond the capabilities of our Newton solver, even though we're using a very good linear solver inside. So that was sort of just the basic stuff I wanted to show about what does linear solver, the basic linear solver stuff look like in PETSc. I have, okay, go through my slides because I kind of put the hands-on stuff in there in case the stuff wasn't working. Okay, so what I want to talk about now was, okay, so we talked about and showed a little bit in the hands-on examples. We talked about inexact versus exact, about using a good preconditioner, and then we saw what happens as we increase the strength of the nonlinearity. Using a good preconditioner can get you pretty far with that, but eventually you run into problems. And so what I want to talk about is some kind of neat stuff in PETSc that was added a few years ago to support nonlinear composition and preconditioning. And I will talk about what that is right now. So I got to start by introducing some definitions and notation. So our prototypical nonlinear equation is of this form, f of x equals b, and we define the residual like so. And then I'm going to use this notation where we have an iterate x sub k plus 1 equals script m, and then I've got a function, a nonlinear function f, an iterate x, and a right-hand side b for the action of a nonlinear solver. So nonlinear, I'm going to talk about both nonlinear composition and nonlinear preconditioning. So a nonlinear composition just consists of a sequence of two or more methods that we just denote script m and n, which both provide some approximate solution to our nonlinear system f of x equals b. So thinking back to the linear case, application of a stationary solver by defect correction can be written like this, where P inverse is a linear preconditioner. Now this is just Richardson iteration in the linear case applied to a preconditioned system. So you'd see this early in a textbook on iterative methods for linear systems. So an additive composition of preconditioners, P inverse and Q inverse, weighted with alpha and beta, can be written out like this. And you can actually come up with an analog for this for the nonlinear case, where we can write out an additive composition like this. And I don't really expect people to digest all this right now. I'll refer you to the paper that describes how this works in PETSc. But you can also do multiplicative combinations of these. So a multiplicative combination of the linear preconditioners can be written out like this sequence here. And analogously for the linear case, we have this m, and then there's the n being applied in here, which just simply indicates that we update the solution using the current solution approximation we've got in residual with the first solver, and then we update the solution again using the resulting new solution and new residual with the second solver. We can also do something that is analogous to preconditioning that some of you may have seen in the Trollinos talk earlier today for linear systems. So if we recall that the stationary iteration for our left preconditioned linear system looks like this. And since a times x sub k minus b equals the residual, for the linear case, we can write the action of our solver n like this. And then if we do some slight rearranging, we can express the left preconditioned residual as this expression here. And then generalizing to the nonlinear case, the left preconditioning operation provides this modified residual of this form. You can also do right preconditioning like so. In the linear case, right preconditioning looks like this. Analogously, we can define the right preconditioning operation in the nonlinear case like this. And I will note in the linear case, the above actually reduces to this expression here, but the inner solver is applied before the function evaluation, which in the linear case is a matrix vector product. So we retain the name right preconditioning, even though it's not really a perfect analog. And there's a bunch of different things that you can do combining nonlinear composition and preconditioning. There's a table that is incomprehensible with what I've just told you unless you go and look at the paper. There's a link to the paper in the slides if you want to look at it, and then you'll explain this table, and it will talk a lot more about the kinds of things that you can put together using nonlinear composition and preconditioning in PETSc. And the reason why I talked about that was it turns out if you use this stuff, you can actually solve some incredibly difficult nonlinearities without having to do things like resort to, say, if you're doing this inside a time stepper, resorting to like really small time steps to get well-conditioned systems. You can actually avoid a bunch of that. Okay, so going back to the examples, we got to a point where just using plain Newton, even with a really good preconditioner or a direct solver for the linear solve, just couldn't make progress. So let's try combining that Newton solver with another nonlinear solver. So we're going to try nonlinear Richardson iteration. That was the thing I started on the first slide with, just saying like, hey, here's the simplest possible iterative method for solving a system of nonlinear equations. Let's try combining that with Newton's method. We're going to actually try that and use Newton's method as a preconditioner for that. So there's this big long expression here that we can try running. Okay, so let's see what happens when we try this. Remember, this was failing before when we were just using Newton. Okay, and here is the danger of doing live live demos, because this is failing, and let's see, I don't think it was supposed to fail, or was it supposed to fail? I can't remember. Let's see. Oh wait, no, sorry, that was supposed to happen. Okay. All right, so trying that didn't help at all. Okay, that didn't work, but let's try. Let's see, what am I going to do here? Okay. Let's actually try doing the same thing that we just did. Like we're going to try to eliminate, like, is this a problem with, nonlinear Richardson and Newton combined together themselves, or is it just a problem with what we're using to solve the inner solve, right? So basically to debug things and figure out, is it a problem with my linear solver, we'll just run with LU. Okay, and so that time it actually converged really quickly. Remember, when we were just using Newton and we switched to using LU, it still failed. But now we're able to do this with this combination of Richardson and Newton. Oh, okay. So we were able to get a little bit farther with Newton alone using that combination we just had. So let's increase the Grashof number just a little bit more. So we were running at like, where was it? Okay, so we were running at like 1.3373 e to the fourth, and let's try that. So we just increase it a little bit more and see what happens. So it looks like, it just, the Newton solve, or our combined nonlinear solver is still, it just stagnates here when we just increase the nonlinearity a little bit more. Okay, so what we were doing before was we were using nonlinear Richardson, preconditioned with Newton. Let's swap the order around, and let's try preconditioning Newton with nonlinear Richardson. So let's do this. And here I set the the max iterations for the SNES solver to a really high number. I set it to 1,000 because I know this takes a long time. But each SNES solve itself is pretty fast, so it's maybe okay to do a whole lot of those. And you see we are making steady progress in the function norms. And okay, after 350 iterations, we've converged. So just swapping the kind of, which is the preconditioner and which is the kind of outer method helped us out. Okay, so we did that. And okay, it did eventually work. It took 350 iterations on theta. When I tried it on my laptop, it took 354. So we could try upping the number of iterations of the inner nonlinear Richardson solver. So we're going to try this. So let's see. Before we were using Richardson as a preconditioner, but we were just doing one nonlinear Richardson step as that inner solver that's our preconditioner. Let's try doing the same thing, but we've increased that to where we can take up to 3 nonlinear Richardson steps. And wow, just adding those 2 more steps inside our preconditioner makes this converge a lot faster. Oh, I keep going back to this. And yep, same thing on my laptop. All right. So then an interesting thing to try is, what happens if, we did a lot better with using 3 or a max of 3 Richardson iterations in our nonlinear preconditioner. What happens if we try messing with this? Like we'll try 4. Interestingly, okay, it actually did, it did worse when we did 4. So that's an interesting thing about these nonlinear compositions tend to be they can be very powerful, but they're also a little bit fragile. And right now, this is actually a kind of newish thing that's not explored in the literature that much. And we don't really have good theory to guide how we should choose these things. So, I tried allowing 3 Richardson iterations for the nonlinear preconditioner. It worked great. 4 and 5 then failed. I ran with 6. It works even better. It's kind of hard to predict what will happen. So it's interesting. It's an interesting numerical analysis kind of thing. These are kind of practical, but they are fragile. So let's see. You can push these really far, though. Like for instance, okay, I'm going to run this command here. All right, so I'm going to run basically the same thing we've been running. I'm running with a nonlinear Richardson preconditioner. I'm allowing 7 iterations on the inside. And I am actually going to push the Grashof number to 1 million, which is an incredibly high nonlinear problem. I don't know of really any other solvers that can solve this problem. And we're going to use PC type LU just to eliminate any issues with the accuracy of the linear solve. And let's see if this is able to solve this problem. It was able to solve it on my laptop. I'm not sure if it can solve it on theta because there are, again, I mentioned these methods are a little fragile and little differences just in order of operations sometimes can make them diverge or not. But okay, actually this worked really well. It was able to do it in 70 iterations. I guess it's hard to put this into context, right? Because most of you have not messed around with Newton solvers solving these kind of problems. But this is an incredibly difficult nonlinear problem, and I don't know of any other solver that can solve this than what we just tried right here. So it's actually, it's really pretty cool that you can do this. All right, so I am going to say, okay, so that's kind of like the main thing, the main things that I wanted to show with PETSc and nonlinear solvers are just sort of, what it looks like, what the basic options are, how to query what the solver is doing by using SNES view. I wanted to talk about the importance of making sure that you not only have a good nonlinear solver, but you have a good linear solver for those linearized systems that arise in a Newton-type method, and the importance of, if at all possible, having some kind of multi-level method that gives you mesh-independent convergence for your linear system. All these things are pretty important, and that's kind of like the main things with the basic Newton solver stuff. And then I wanted to show that PETSc has some fairly recently introduced, actually it was introduced I think about 5 years ago, but it hasn't really been explored. The postdoc who mostly worked on this then left and got a job with Google, and people haven't used it that much, but it's there. And if you are solving really difficult nonlinear problems, I really think these are worth looking into, but they're not very well explored in the literature. If you do Google searches for these, there just aren't many papers on it. The people using this stuff is kind of new, but I think it's a really cool thing that I'm excited about, because I work on a lot of problems where you get difficult nonlinear systems, and I think they're pretty neat. So takeaway message for this main part of the talk was that PETSc provides a wide assortment of nonlinear solvers through its SNES component. It's not just Newton. You can build really sophisticated solvers from composable algorithmic components. So we have like inner linear solvers. Your Newton method can employ a full range of solvers and preconditioners provided by PETSc's KSP and PC objects. Multi-grid solvers in particular are important for mesh size independent convergence. PETSc's got a lot of stuff to do different kinds of geometric multi-grid methods. It's also got a native smooth aggregation algebraic multi-grid that can be good for some problems. And then if you want to use a good classical algebraic multi-grid, then you can use something like Hyper, which interfaces very well with PETSc. I use Hyper's Boomer AMG solver with PETSc all the time. You can also, analogously to building this for the linear solvers, you can also do this with the nonlinear solvers. You can combine the SNES solvers just like you can combine the PETSc, KSP, and PC linear solvers. Today, most people are still using Newton-Krylov type methods, but there is this large design space of composed nonlinear solvers to explore. I think I just kind of already advertised that. It's a cool new thing. I think it's pretty promising for some problems, but they're pretty frustratingly fragile. The one rule of thumb is that I've found that like nonlinear Richardson, Gauss-Seidel, or nonlinear GM-Res combined with Newton somehow often does improve robustness for your solver. There are a lot of other things that could be explored if you have nonlinear solver problems that you want to look at. There's nonlinear domain decomposition algorithms in PETSc that I didn't talk about. There's also nonlinear multigrid or full approximation scheme methods. The multigrid that I showed you was multigrid for the linear solve that arises inside Newton. So you do Newton method, then for your linear system you have a Krylov method, and you precondition that with a multigrid method. You can actually do multigrid where you're actually applying multigrid to the linear system, and your smoother is the Newton method. You can do this in PETSc with the SNES FAS method, full approximation scheme. I also note that PETSc time steppers use SNES to solve the nonlinear problems at each time step. And there's also one of the time stepper components we have is a pseudo-transient continuation problem that can let you solve highly nonlinear steady state problems. So that's it for just my talk about PETSc SNES. But because everybody is interested in doing GPU computing these days, I did want to talk about how you can do this in PETSc as well. Let me switch back over to some slides I made. I'll talk just a little bit about that. Okay, yeah. So really, the meat of my talk was just about what's a Newton method? What are some of the other iterative nonlinear solvers? How can you use those in PETSc? And that discussion is really kind of it's mostly orthogonal to the topic of how to run PETSc solvers on GPUs. But since computing on GPUs has become really important in the last several years, I added some extra content where I'm going to take a brief look at the GPU support in PETSc and how you can use that to in the nonlinear solvers and execute those on GPUs using the PETSc backends for that. I'll talk just a tiny bit about how PETSc uses GPUs. So the way we've added GPU support in PETSc for its solvers is that we've decided to add several new implementations of PETSc's VEC, that's our distributed vector, and MAT, our distributed matrix classes, which allow data storage and manipulation in device or GPU memory. We actually just use like what we call a lazy mirror model here. So we imbue all vector and matrix objects with the ability to track the state of a second offloaded copy of the data, and we synchronize these two copies of the data only when required. So there are several good reasons that we do this. One is that there are certain kinds of operations that you might do on a vector or matrix that are not things that are very performance critical, or things that you don't do very often, and it doesn't make sense to actually have a GPU implementation for every single thing you can do with a PETSc vector or matrix. So doing things this way, we can fall back on CPU implementations. There are also some things actually, just because of the way a GPU is organized, it's very hard to do well on a GPU, so we want to be able to use the CPU sometimes. And so we just keep, if we have a PETSc vector that we're using on a GPU, we keep a CPU copy and a GPU copy. We keep track of the state, which one's fresh, and then when there is up-to-date information on the GPU and we call an operation for which we've got a GPU implementation, we do it. So to actually use the GPU backends in PETSc, basically all you have to do is via runtime options, you just tell PETSc that instead of using like my normal CPU-based matrix classes, I want you to use these GPU ones. So actually you just add command line options, like you say, hey, if I'm running on an NVIDIA machine, I want to use CUDA. I'm going to say my matrix type is AIJ. That's AIJ is PETSc's compressed sparse row format. That's their standard thing. AIJ is what you get when you the standard AIJ matrix runs on the CPU. We've got a version of that that's AIJ cuSparse, where it uses the NVIDIA cuSparse library to do some of the operations. And we say my vector type is CUDA, or if you're running on an AMD system, you could do that with Cocos. And you say your matrix type is AIJ Cocos, vec type is Cocos. And it's really as simple as that. Now, because PETSc is designed in this hierarchical, has this hierarchical organization I showed at the very beginning, where our SNES solvers sit on top of KSB solvers, and those use the MAT and VEC operations. Basically, anytime you've got some operation that happens inside your nonlinear solver, this eventually trickles down to things that are implemented in the VEC and MAT classes. So if you say I want to use a Newton solver, and I'm using the vector and matrix vector and matrix types that are associated with GPUs, all of those kernels are going to run on the GPUs, and that's how you do it. So I thought I would talk some, just show how this works on Theta GPU, since we've got a GPU machine. So this is totally like the extra credit part of this. So okay, first thing I want to do for the hands-on part is I want to unset PETSc options. We had set a bunch of things in there, but I'm going to just unset those so we know exactly what it is that we're running. So unset that. And for this part of the example, I'm just going to take the same driven cavity problem that we've been doing, and I'm going to run a very large version of it. Like we had been running up to 4 refinements in generating the mesh. We're going to refine it 9 times. So we're going to run that. We're going to use multi-grid. In this case, I'm going to use as a solver, not the default multi-grid solver in PETSc, multi-grid smoother. The default is an SOR smoother, which is not friendly to GPUs or SIMD architectures. So instead, we're going to use a Chebyshev Jacobi smoother with that. And I'm going to collect a breakdown of the timings by multi-grid level by adding this option PCMG_log, which is going to log this performance in a text file. So I actually already know that you really get basically the best performance running this on Theta GPU with 8 MPI ranks, and I'm trying to run on the CPU. When you're running on a single GPU interactive session on Theta GPU, you actually get 16 CPU cores, but you can't actually use the 16 cores effectively on a problem like this because there aren't enough memory channels for those cores, and eventually you just saturate the available memory bandwidth. So you could try running the same thing with 16. Nothing bad happens. It just doesn't really run any faster than with 8. So So I'm running with 8, and this will take a little while because this is a pretty big problem. It should take like a minute or two to run. Let's see. I thought it would run faster than this. Is it doing anything, or did I get kicked off of my interactive session? I wonder. Okay, so it finally ran. And now I'm going to run the exact same problem, except I'm going to run it using the Theta GPU that is attached to this session. So you see I'm running basically the same command here as above, except in this case I'm only going to run on one MPI rank, and I am telling this that I'm adding this DM vec type CUDA. So DM is the domain manager that manages our parallel domain. I'm telling it any vectors generated associated with that should be of type CUDA. Any matrices generated using that DM should be of type AIJ cuSparse. And then I'm again going to write this to a log here. I will note I'm only using one MPI process here, and that is actually because Theta GPU is not running something called NVIDIA's multi-process service, which is a service that NVIDIA that you can run on an NVIDIA system that multiplexes a bunch of different GPU calls from different MPI ranks. If I were running that, I'd be able to run on more MPI ranks and it would work well, but it's not running that, so I'm just running on the one. And let's see, that did run faster, I'm pretty sure. So let's see. Let's see here. I'm going to open up these log files that I generated now. Oh, now is when I really wish I had. Well, let's see. Will this work if I'm going to make the font smaller, actually. Okay. That's going to be pretty hard to read, maybe, but I think people can see that. Okay, so at the top I have the, oops. Did I, oh, sorry, hold on a second. There we go. Okay, so I've opened up these the PETSc log files, the text versions that we just generated, and in the top half of the window, I'm showing the results for the CPU-only run, and in the bottom one, I am showing the results for the GPU. You see this time summary. This is the thing we've been grepping for. I'm taking 24 seconds in the GPU case to run it, and 62 in the CPU case. So I am getting some speed up with the GPUs. So let's see, what did I have we wanted to try looking at in here? Okay, so let's just see, what I highlight in here in the hands-on. So yeah, opening up a log view file shows us a lot of data about the performance. There's the useful overall summary at the top, which is what we're looking at here. Then there are also timings for a bunch of events that occur during different stages of the computation. So if we scroll down, there's a whole lot of stuff in here. There's the two stages. There's a main stage and then a separate stage just for the application of the preconditioner, which I'm getting because I'm running with PCMG log, so I'm asking PETSc to break that out in a separate stage. So there's that information, and then there is a ton of stuff in here about all these different events, like mat-mult. That's a matrix times vector multiplication. I can see things like how many times it's happened, how long it's taking, and when you've built PETSc to run on a GPU, you get these extra columns added over here where there's like a GPU megaflops per second number, and really important are the CPU to GPU transfers and GPU to CPU transfers, because this is really important to keep track of, like, am I spending too much time shuttling data back and forth between the CPU and GPU. And then also at the end there is just a percentage of flops for this event that happened on the GPU. So all of my matrix vector multiplies, 100% of those are happening on the GPU. So this at least tells me it's doing what I think I'm trying to tell it to do. So there's a whole lot of stuff in here, and a lot of it is very useful and edifying when you are trying to figure out your PETSc performance, but I don't really have time to look at that right now. And you'll see actually it is very hard to look at this and tell, like, well, what is the relationship of a bunch of these things to each other? Because, like, in here, the SNES solve is really, this tells us the time that's really required to do the entire SNES solve. So this is really the part that's not just starting up the PETSc executable. The part that's really the solve, the meat of our computation, is all contained in this SNES solve timing. But we know the SNES solve is solving a bunch of linear systems, so there are these KSP solve calls that happen, and all the KSP solve calls happen as part of the SNES solve. It's hard to look at this and know what this really is. And so there is actually a very cool way to actually get something that's a little easier to interpret. And so I will actually, I'll just run this again. I'll run the GPU case first. There is a way to get PETSc to, instead of just writing out these text files, which are themselves pretty useful, I can ask it to produce a call stack of the PETSc events that I can plot as a flame graph. So if you were able to follow along, take those two commands in there for generating a flame graph and run them. And I got to run the whole problem again. And it's going to generate this file that I can feed to Brendan Gregg's flame graph tools, or speedscope.app, which is a web tool that is what I'm going to use right now. So we ran that one for CPU, or for GPU. Let's run the same thing for CPU. And so I'm running these, and I'm running a little short on time, so I'm going to cheat because I already ran this and downloaded these. But what you should do is, if you're doing this yourself, you're going to generate these files like log mggpun1.stack. Download these .stack, just SEP these .stack files to your machine, and then you can go to speedscope.app. That's the URL. So you go to speedscope.app. You will be able to open these up in a very cool flame graph style thing, where this gives you a hierarchical view. Actually, it'll open up in time order like this. It'll open up in time order where it actually tries to sort of like plot things as they show up in the logs, which sort of has to do with their execution time. But I'm actually just going to click on the left heavy where it sorts everything so that the most expensive things show up pushed to the left of this graph. So you see like 98% of our CPU run here is in the SNES solve. And then you can see, like, okay, KSP solve happens, and that takes like 74% of our time. All of the SNES solve is happening inside, all the KSP solve is happening inside the SNES solve. And then the PC apply happens here. And then under the PC apply, because we've asked PETSc to break down what's going on with the multigrid solve in its logs, I can see things like MG smooth level 9. So we're running 9 levels of multigrid. Actually 10. We're at 10 levels of multigrid because there's 0. We're C programmers. And you can see the smoother operations in here. And like, level 9 is taking up a lot because level 0 is the coarse solve, and that takes almost nothing. And the fine level solve is what takes a lot of time. So, we spend a lot more time in MG smooth level 9 than we do in, say, MG smooth level 8. And you can zoom in and out, by the way, in here by just using plus and minus on your keyboard. And then you can drag this window around and zoom in and out on what's going on. The thing that I wanted to show, and unfortunately I don't think I have the screen real estate to do it here, it's just not high resolution enough, was I wanted to show the CPU and the GPU ones together, but I really need a higher res display, so I'm just going to go over to the GPU one. And let's see, I'll zoom all the way back out, go to left heavy, SNES solve, and what I want to show that's a kind of interesting thing that tells you a little bit about GPU architectures versus CPU architectures is I wanted to zoom in on these MGs, where'd it go? Let's see, I'm lost. Okay. These MG smooth steps. So if I look at the time spent on smoothing inside these, and this is on the GPU, okay, I spent a lot of time in level 9, that makes sense, slightly less than half in level 8. But if you go here and you look at the coarser levels, once you get down to like level 6, level 5 only level 6 only costs a little bit more than level 5. And if you look at the cost of the course level starting from level 5, going to level 4, level 3, even though each one of these levels, like MG Smooth, the level 2 of the solver is really small compared to the 5th level of the solver, but I'm spending the same amount of time in each one of these. What you're seeing here is the high cost of a kernel launch on a GPU. GPUs are really very throughput-oriented architectures, as somebody probably already told you earlier in this workshop. And you can really just see it right here. And the cost of all of these very small solves is constant, because the cost of like running your smoother on level 1 of the hierarchy is entirely dominated by the cost of that of just the kernel launch. And if you compare that with the CPU one, you will not see that. You'll see that as I zoom in on these multi-grid levels, like each time I go to a coarser level, it really does take a lot less time. That's because the CPU gives me a lot worse throughput than the GPU, but it's got much better latency. So it's pretty cool to explore these two things side by side. I'm out of time, but there are some more things I wrote in the hands-on exercises if you want to explore sort of, what about using GPUs is good for this, what's bad. There are some cool things to explore with that and a few other things to try. You can follow the instructions and try running with a different back end. I ran with a CUDA one. There's also a Cocos one you can use. And also it's very interesting for people who want to try it to run with W cycles instead of V cycles. So I ran this example with V cycles. So I start at a fine level, I go all the way down to the coarse level, go back up to the fine level, and so I visit all these levels kind of, about with the same frequency. A W cycle starts at a fine level and then goes down to coarse levels, and then it spends more time on the coarse levels, and you really start to see the differences in what happens on a GPU versus a CPU when you run this different kind of multi-grid smoothing, this different kind of multi-grid cycle. It's going to spend more time on the small problems, and it's neat to compare these and ask some questions about where are the things where the GPU really excels. Because you'll see things in here when you compare these where the GPU really speeds up some operations and does not speed up others. In fact, is slower on some of them. It's a very neat way to compare these visually interactively using these flame graphs in the SpeedScope app or any other flame graph visualization utility. And with that, I am just about out of time, so I will stop and take questions. And then after that, I think there's a break, right? Yeah, so feel free to talk to me during the break too if you've just got something you want to talk about, but not ask in front of the whole crowd. All right, so thank you.